JavaScript is extremely popular. GitHub's top 10 chart shows it's been in the #1 position since 2014. I respect developers who become proficient with it, but it isn't everyone's favorite language. There have been many efforts to provide different options, from alternate runtimes like Flash and Silverlight to languages that compile to JavaScript like CoffeeScript, PureScript, Elm, ClojureScript, and TypeScript, to name a few. WebAssembly opens things up dramatically, but currently it can only access the DOM through calls to JavaScript. Objective-C held the 10th place position until 2017 when TypeScript replaced it, and TypeScript continues to climb, currently in 4th place. TypeScript is the first language to reach GitHub's top 10 list in only 5 years. Instead of creating a completely new language, Microsoft took the interesting approach of making TypeScript a strict syntactical superset of JavaScript, so any JavaScript file is valid TypeScript. Essentially, TypeScript is JavaScript with additional syntax that specifies the type of variables and expressions. The TypeScript compiler, or more accurately transpiler, validates that the types of expressions are used appropriately and safely. The compiler's output is pure JavaScript, most of the time looking very similar to the TypeScript source. So why has TypeScript exploded in popularity? In my experience, it solves every problem that I've had with JavaScript. In 2013, I took a course on the then popular Knockout web framework. I decided to use the latest version of the Knockout library, even though the course was over a year old, thinking that working through version changes would be a good exercise. It was, but it was very frustrating, since the very central configuration object had been completely restructured. The presented code silently failed to work. In typical JavaScript fashion, the configuration object could be very flexible, supporting various shapes, so the documentation had to be interpreted very carefully. Any errors, and it simply failed to work without helpful error messages. I remember even tediously stepping through the framework's code to see what was going wrong a couple of times. Programmers have to work through tough issues all the time, but comparing it to my experience with all the strongly typed languages I'd used so far in my career and the IDE support that goes along with them, dynamic typing created unavoidable problems, in my opinion. As you'll see, TypeScript lets you access the flexibility that dynamic typing allows, but in a type-safe way. It even has many powerful typing features I've never seen before. So, are there other benefits? Strong static typing is the main feature of TypeScript. Catching common type or spelling errors at compile time instead of runtime is very beneficial. There are many features that give you control over the level of type checking you desire. The developer can buy into different levels with compiler settings and language features. Even though adding extra type annotations is a little extra work, it just keeps giving back. While coding, your IDE will help you with autocomplete, particularly useful when traversing large data structures, or shows the signature of method you want to use. This eliminates time you would otherwise have to spend checking documentation or browsing other module source code. It keeps paying off as different developers work on the code over the years. And code with type annotations is self-documented, easier to read and understand. ECMAScript 2015 added support for classes, but TypeScript provides a few syntax improvements, and interfaces are also a very powerful feature. Access restrictions on class members creates more robust code. And if the JavaScript runtime you're targeting supports modern syntax, like class definitions, for example, the resulting JavaScript will be almost identical with type annotations removed. But if you need to support an older runtime, TypeScript will generate equivalent code for that runtime. This means you can use the latest JavaScript features and syntax, and the TypeScript compiler will take care of translating it into functionally equivalent code. So this video is not going to thoroughly cover TypeScript. There are many excellent tutorials and other resources that do a good job of that. I'd recommend starting at TypeScript's official website, typescriptlang.org. clicking the Docs link is a good place to start. This page has links to all the other resources on this site, getting started guides, the handbook reference, and more. Now the playground lets you see how TypeScript is compiled into JavaScript. The very useful examples dropdown shows working code with lots of comments. So let's say, you want to look at functions. It's got a lot of comments and examples. And on the right, you see the JavaScript that results. Or in the case of, where the typing, catches errors, it shows the errors. And let's say, if you want to look at, generics, I find the examples is a really handy place to get a quick overview of a concept that you want to refresh. So the purpose of this video is to show you that you can probably just start typing JavaScript into a TypeScript source file and add type annotations where they are needed. And I'll cover some specifics of using TypeScript with the Solid framework in the next video that builds a small web application with them. So let's continue using this playground. So here are our 3 class definitions. And I'll cover type annotations in a minute, but I just want to show how the TypeScript compiler configuration can change what JavaScript gets generated. The first 2 classes are written with valid ECMAScript 2015 or later syntax. The resulting JavaScript code just has the type annotations removed. See, they're pretty much identical. The third class is very similar to the first, but it uses some convenient syntax that makes the code more concise. That is, specifying an access modifier before the constructor parameter name. You can make this public, protected, or private. Now it does 2 things, extra things. It declares a class member with that name and type and automatically initializes the instance member from the past constructor argument. So notice that the resulting JavaScript for the first and third class are identical. So I was just showing that, mostly TypeScript adds, type checking and static typing, but it also has some small syntax, convenient syntax, here and there. So now let's open this dropdown tsconfig shows the TypeScript compiler configuration. Now the target ECMAScript version is 2017, that it defaults to that. Now if you target 2015, the resulting JavaScript code won't change because ES 2015 supports this class syntax. But ES5 did not support classes. So the compiler generates equivalent code, but it's much harder to follow and understand. But it's nice in that if you want it, you need to target browsers that don't support ECMAScript 2015. You can do it, and your TypeScript code will work, the way you expect. But you should target the latest ECMAScript version possible because it will generate less code, and the JavaScript runtime can better optimize the more expressive. Let me change this back to 2017. It's easier for the JavaScript runtime to optimize this more expressive modern syntax, and which one you choose depends on your supported browser versions that your clients use. The TypeScript compiler has a number of other options that control how strict it is with type checking. I enabled them all since I come from a background of strongly typed languages and want to go all in on safe code. You can turn some off if they get in the way of JavaScript flexibility that you're comfortable with. The JavaScript language spec has some quirks related to the this keyword and the scope of variables defined with var. As far as I know, there's no reason to use var anymore, so just use let and const. Const being for variables that are assigned once and never get reassigned. There is still a lot of complexity to the language because of backward compatibility mixed with many new features. Arrow functions allow very concise syntax and have more intuitive scoping and this binding, avoiding the need to define that equals this or call bind. If you are new to arrow functions in JavaScript, I recommend you read a fairly short article that explains arrow functions and where they make sense and where they don't. Find a link to it in this video's description. So let's see some simple TypeScript code. Now, by the way, semicolons are optional in JavaScript, and I'm so used to typing them that I frequently, forget that I can leave them off, so I may do it either way. So even though this code doesn't have any type annotations, the compiler infers types from usage when it can. So see that the compiled JavaScript on the right is identical. Now when we rest our pointer on the variable x declaration, the editor interfacing with the TypeScript compiler says that x has a type of any. But if we rest our cursor on it after the last assignment, TypeScript flow analysis knows that x is an array of strings at this point. And it knows what the type is after each assignment. If I type x dot, right, what it knows at its point x is a number, and so these are the methods that a number takes. Here it knows that x is a string, and so here's like the substring functions, and this is at this point it's an array of strings, and so you can do a join and things like that. So, we didn't add any type annotations, but type inference identified the correct types. And I wouldn't recommend declaring a variable without a type if you want TypeScript to perform strict checking. If you want a variable to not have type checking applied, you can make it explicitly have a type of any. So let's do something illegal. And so we'll call substring on x, but at this point x is a string array of strings, and so the error property substring does not exist on type string is pretty clear. So this is one of those features where you can tell TypeScript to stop doing type checking by explicitly giving it a type of any. And a type annotation follows the variable name separated by a colon, and the convention is to put a space after the colon. Now this seems to be identical to the declaration without a type annotation because, as you saw, x was given the any type, before. But this is very different. A variable declared without any type annotation seems to tell the compiler to figure it out, any being the only valid type it can determine before the variable is used. Explicitly providing a type of any tells the compiler to skip all type checks for that variable. And you can see it stopped reporting the call to substring as an error, but that didn't fix it. So I'll open the debugger tools. Let's clear the console log, and if I run this application, you can see when it runs, it gets this error: substring x to substring is not a function. So, and I'd recommend against explicitly declaring any variables any, but there may be rare cases where this is appropriate, particularly when calling external libraries that don't provide a type definition file. More on type definition files later. There is a compiler option, no implicit any, that tells the compiler not to assume the any type when a type isn't specified. This option is turned on here, but it doesn't seem to apply in the simple case where a variable is declared. But it will complain about function parameters without types. So you see it says it can infer the type of arg, and we've turned off this option to assume anything that doesn't have a type as any, so it can't work with that. So, and I'd recommend always turning on no implicit any in your project, particularly for new code. But if you're converting a lot of old JavaScript code to TypeScript, turning that on would force you to add a lot of type annotations right away. If you want to convert your code slowly, turn no implicit any off, and then you add type annotations over time and turn it on when the migration to TypeScript is finished. So let's see. And we can, fix this by giving it a type. And it makes the error go away. So let's give x a variable type. Say that it's a number. Now it doesn't like that we are setting it to a string or a string array. However, as I said, using TypeScript doesn't mean you miss out on the flexibility of JavaScript. If we want x to support being set to any of these types, we can specify a union type. This says that x can be set to any of these three types. And you can see the errors went away. So does this eliminate the benefit of strong typing? So let's use x as a number. Now, the compiler knows at this point of execution, x is an array of strings, not a number that math round expects. So if we move the numeric assignment to be last, let's see, so the error is saying that string array is not assignable to a parameter of type number. So the last thing we do is set it to a number. The error goes away. But let's see what happens when the current type is ambiguous. Now func doesn't exist, but let's ignore that for now. The compiler now interprets the type of x to be the full union type, number or string array. And this type can't be passed to math.round function either. So you must use type guards. So now the compiler tracks that we are executing code that uses types correctly. At runtime, we use it as a number only when it is a number, and we use it as a string when it is a string. And TypeScript flow analysis tracks that we're doing it correctly. Now if we type in the else clause, right? In this case, the compiler knows that the only valid type of x at this point is a string array, and it shows the array's join method is available. So now let's define the func function. So let's digress a little and talk about adding types to function declarations. In this case, the compiler inferred the type of func. The syntax in this pop-up means that func is a function without arguments that returns a number. We could explicitly specify the type for func like this, and really all I changed was that there, inserted that. But that isn't necessary because it matches what the compiler already inferred. But this syntax is a little hard to follow, but you get used to it. You could put parentheses around the type and, maybe that helps. A little, anyway. Generally, arrow functions are very concise, but if you wrote the traditional way, the typing is a little easier to follow. Now let's see what it would look like if we defined a function that took an argument using both forms, the old function syntax and then the arrow syntax. They're basically the same length, but the traditional definition of func1 is much easier to follow. Let's get rid of this. The argument is given a type right where it's declared, and the return type follows the arguments. Now the arrow function makes more sense if you separate it into two parts, everything before the equal and everything after. What's before is declaring the variable func2 and its type, and what is after the equals is what you're assigning to that variable. Now if you declare a variable that will get assigned to specific function implementations later, you have to specify its type. So you see func3, I gave it a type that is a function that takes an argument that's a number and returns a string. So now a type annotation for a function requires the arrow syntax, but that doesn't mean it has to be assigned an arrow function. In the first case here, we assign it to an arrow function and invoke it. But the second time it's assigned to an anonymous function declared with the traditional function syntax. Also note that the type declaration names the argument arg, but the implementations can name their argument differently, arg1 and val. It's also interesting that the argument for the function implementations arg1 and val don't require declarations, right? We didn't have to put types after arg1 or val. Now, by the way, just if you ever do need to give this a type, you have to put it in parentheses. So if I didn't have parentheses and I tried to give this a type of number, which it doesn't understand that, it just is too weird. So you put it in parentheses. That's basically parentheses are required around your argument list when they have type specified. Just a little aside. So what I was saying is it was also very interesting that the argument for the function implementations arg1 and val don't require type annotations. That's because they're being assigned to the func3 variable, which the compiler knows what that type is, so it knows the type of the argument. Now, if we assign that same function to another variable, like a new one that doesn't have a type specified, it won't know what the type of val is and warn you that it will have a type of any. So in this case, you have to specify a type for val. Let's see. Now, this may seem overly complicated, but I found that a good way to start using TypeScript is to just write your code without type annotations and see if the compiler inferred everything correctly, which is easy to check by hovering over the symbols, and then add types where it complains. The compiler rarely gets in the way when it shouldn't. And instead of having to think about which function declaration syntax I should use, with the exception of class methods, I now always declare arrow functions. All right, so that was just a little aside on adding type annotations to functions. So let's get rid of that. And let's change our function back to its simplest form. All right, so type inference determined that func always returns a number. Therefore, x has to be a number. And now when you check the type of x inside the string and string array type guards, it has, let's see, that's the number. So here, it has a type of never. And this is a strange type indicating that it can never happen. This is also the type of functions that never return. So, I mean, this makes sense in that, if x is a number, then these, it can never be a string, and this, it kind of gives x a type of never at this point to let you know that. So now let's change func to possibly return any of the three types that match x's type, depending on the argument passed. Oops. So the compiler inferred that this function can return a number or a string array. So its return value is now the same as the x variable. And if you have a long type that is repeated in several places, you can create a type alias like this. And we'll change our x declaration to use this type. Right. And if you want to add a type annotation to the func function, which is unnecessary because type inference figured it out, but it is a little bit clearer with a type like this. So func is a function that takes a single argument and returns our type. And then we don't need this here, that's redundant. And we can remove parentheses if there's no type annotation. So that's kind of maybe a more formal way to define the function. So now we can run this code to see it in action. And let's see, so it's going to call function with a random number, and depending on the random number, it's going to either return a number or a string array. And then with these type guards, it's going to log the specific data type. So let's hit run. That time it was a string. There's a string array. There's a number, string. No, that was a string array. Number, string array, string array, string array, string. So you can see that it's working. So, the nice thing about this is that you have strong typing. Everything's being used in a safe way, but TypeScript doesn't, make you give up the flexibility that JavaScript provides of allowing things like having a function that returns different types, which I think a lot of JavaScript programmers are used to that sort of flexibility. So far I've just demonstrated primitive types, which are string, number, Boolean, null, undefined, and symbol. But of course there's first-class support for object types. So the curly braces around this person type alias means it's defining an object type. The question mark following first name means that it's optional. First name is optional. So now let's create a person object instance and reference the first name member. Now, by the way, if I did not explicitly say that the variable p is a person, right, it's fine, right? We're just creating a variable and TypeScript will know what its shape is. If we use it incorrectly, even here, you can see that, you know, this anonymous type doesn't have a first name and it knows that. But if we want to, you know, if we know it's a person, we want to give it that type. So, you know, even if you declare an object with the same shape, it doesn't know it's the same, you know, type. So you need to explicitly give it the correct type. And here it's showing us two errors. The first says that age doesn't exist in the type person. Yep. And let's just delete that as I put that there to demonstrate that case. Now the next error is caused by the fact that first name is optional, so a reference to it could return undefined, and you can invoke trim on undefined. So it requires a type guard, either equals string or not equals to undefined will work. Now, as we learned about union types, types separated by the or symbol, there are also intersection types, types separated by the and symbol, the ampersand. And this only makes sense with object types. So we created a new type, employee, that has all the members of person plus location, code, and title. So it's pretty neat. You can kind of augment a type that's already defined. Also, TypeScript will let you restrict variables to specific literal values. So this is saying S has to be red, blue, or green as a string. And so we can set it to blue, but you can't set it to yellow. And here we're saying N has to be 1 through 5. You can assign it to 7, but you can assign it to 1. So this is something I haven't seen in other languages where you can be that specific with your types. So I hope that gave you a feel for how TypeScript will help you write code more efficiently and with fewer bugs. Even though adding the type specifications to the code takes a little time, I think it speeds things up overall when the IDE gives you constant help on the types of your expressions. This is particularly helpful with deeply nested structures, or when the type you are referencing was created in a different module. Now there are a few additional things I'll mention that you can investigate on your own. A powerful TypeScript feature is generics. If you aren't familiar with generics, the TypeScript documentation has a section on it. So if you click on the docs and then the generics section of the handbook, it has a nice write-up about generics. But if you're familiar with it and you just want a refresher, the playground has an example for generic functions. And this is a little bit quicker and kind of a nice refresher. There's also an example on generic classes. All right. So, and it's hard to know what features you will find most helpful, but I want to mention enums and tuples. TypeScript tuples are fixed size arrays with known element types, and I find them very useful. They're covered in the handbook's basic types page. Here's the tuples. And enums, I'm sure everybody's familiar with, but if you want to know how TypeScript specifically does it, you can get there from here as well. So you can see that, you know, this is a good place to start. Look at the basic types if you wanted to know about objects and type assertions and any of these things that I covered in more detail, and you want to know about it in more detail. So the last topic I want to cover is declaration files. And these are files that just contain type declarations. So let's go back to the playground. So on the right, it can show the resulting JavaScript. But if I click on the .d.ts tab, it will show type declarations instead. And so as you can see, this doesn't contain any JavaScript code. It's just our type definitions. And this is a TypeScript specific syntax. It basically declares all our types. And so you can see that func over here is defined as a function that takes an argument as a number and returns our type, and it shows what our type is. So type definition files are helpful when you're using an external JavaScript library. You want all the goodness of autocomplete and type checking calls to that external library, but your IDE shouldn't require access to all their source code. So they can provide a type definition file along with their JavaScript library. The type definition file contains everything your IDE needs to provide autocomplete and type checking. And if an internal library is written in JavaScript, the type declaration file with an extension of .d.ts has to be written by hand. If it's written in TypeScript, the compiler can generate the type definition file. And library providers will typically bundle a type definition file with their library. And this is all automated by the node project dependency mechanism. If you obtain a library outside of a node project dependency, you can frequently find a high-quality type definition file on the website definitelytyped.org. So I'll search for definitely typed. You can find type definition files for almost any library here that people have created, and they're high quality. And you'll see that when we use the Solid UI framework, Visual Studio Code will know all the types used in their API just by making Solid a project dependency. The node project will take care of downloading the library and the associated type declaration file. And Visual Studio Code will find that type declaration file automatically. In the last video in this series, you'll see how I wrote a simple type declaration file to integrate TypeScript code into a large JavaScript application.